Hi guys, welcome to another episode of Chem Complete, and we are going to be working on the general chemistry lecture portion today. We're going to start talking about quantum mechanics. So the first thing I want to bring up is this idea of quanta, and what is quanta? So quanta is essentially we're looking at discrete energy units when we're working with quanta, and that's where the definition for quantum mechanics comes from. It was very peculiar because back in the 1900s, the early 1900s, you had several people like Erwin Schrödinger and Max Planck and Albert Einstein that were investigating why atoms were behaving the way they were, particularly when it came to light and electrons and energy. And what they found was that when atoms give off some level of energy, they seem to only be able to give it off in discrete chunks, or what you would call energy packets, right? So you have one low level energy, what we could call energy 1, and then you'd have energy 2, energy 3, and you keep climbing up the rung, right? So what we're saying is if there was some sort of an electron excitation and then the electron fell back down to a lower energy level, it would have to emit some energy out from the atom. And what they found was that atoms could only emit these quanta or discrete energy units. They couldn't have a continuous energy scale that they were able to give off, right? So you couldn't start at energy 1, and anywhere between energy 1 and energy 2, the atom could give off some level of energy in between there. It was either the atom gave off energy level 1 or it gave off energy level 2. There was nothing in between, which was kind of bizarre. We didn't think of it that way until they started to discover this stuff in the 1900s. And there was a lot about quantum mechanics that kind of turned Newtonian physics on its head when we were working with that. So one of the other things that we came to find out was that light ends up behaving as both a particle and a wave. And this was very bizarre because you usually thought of it was either one or the other. So some people made the argument that light is an individual particle, right? So it's a photon. It's these tiny little particles that you can kind of bombard anything with. And that's what light was. It was really just packets of these photons that could be individually counted. And other people came along and they said, no, look, we can prove that light acts as a wave, right? A continuous wave that's going along. And so there were these conflicting results that kept coming out. And so what was designed was something called the double slit experiment, where they took a box, if you imagine almost like a shoe box, and they had a filter in the front that had two slits. And through those slits, they shined a beam of electrons, right? A beam of light, essentially. And what they found was that the pattern on the back of the wall of that box alternated as light, dark, light, dark, light, dark. So just think of it almost like, these alternating patterns of a bright spot that's a line and then a dark spot that's a line, a bright spot that's a line, a dark spot that's a line, right? And so what that told them was that, oh, light must behave as a wave because those dark spots were waves that had destructive interference with one another. They were canceling each other out. You don't see that kind of behavior when you end up having individual particles, right? So they said if we had individual particles, what we would see is at the back of the wall of that box, we would see these two slits that have a lot of light where the particles, the photons, are hitting, and then the rest of it would all be dark, right? But when we see that alternating pattern, it means the waves must be traveling and spreading out, and you get the alternating light, dark, light, dark, light, dark pattern. That can only happen with waves. So then they turned around and they said, well, what if we were to just measure the light, the photons, before they traveled through and hit the other end of the detector on the other end of the box? And so they did this. They took essentially a laser beam, and as they were passing the photons through, the laser beam caught those individual photons as they passed through the slits. And lo and behold, when they did that, they found that the pattern changed. And this is very bizarre. It changed to those two slits that had all the light photons concentrated in that area, and the rest of it was dark, right? So what's so weird about this is that when you're talking about the double slit experiment, it depends on how you're setting up the measurement. So if you're observing the light in one fashion, it's acting as a wave. And if you're observing it in the other fashion, it's acting as a particle. And this is very bizarre because what it tells us is that light is both a wave and a particle at the same time until you measure it. Because once you measure it, it can only be a wave or a particle at that given time. And this was sort of the prelude or the lead-in to a whole series of bizarre experiments that ended up defining quantum mechanics in current day. And so a lot of people hear of Schrödinger's cat. Schrodinger's cat was an attempt to explain how the cat, a lot of people have memes about this online and they talk about it. The cat is alive and dead at the same time when it's in the box. That's the same thing you're talking about light. So light is acting both as a wave and a particle until you observe it, and then it can only be one of those two. And that's what's so weird about the quantum universe is you can exist in multiple states until you've actually been observed. And then once you've been observed, the quantum universe starts to break down and we enter into the macro classic Newtonian type universe, which is where the bulk of our understanding has been throughout history. We're still very much on the new edge of quantum mechanics as we're learning this sort of stuff. So enough about Schrodinger's cat. Let's talk about the math because we're going to need this for general chemistry, right? So the thing I want to talk about today in terms of the math is a couple of things. We're going to talk about a few variables here. C, this is lambda, all right, which is a Greek letter, and then this is not V because it's got the edge to it. This is nu. Okay, so this is lambda, and this is nu, Greek letters. And what these represent, lambda represents wavelength. We'll talk about what that means in a second. And nu represents frequency. All right, so C is the speed of light. Now, one of these three are constant, and hopefully you realize that what is constant out of these three is the speed of light. So a light wave can have differing wavelengths and frequency, but the speed of light is the speed of light. So the speed of light is not going to be changing, and that value is 3.00. This is rounded approximately. It's like 2.999 something. 3.00 times 10 to the 8th meters per second. Okay, that is incredibly fast. So much so that we have not discovered anything faster than the speed of light. Time and a bunch of other dimensions and everything that we perceive is based on the speed of light. This is, if you're talking about physics, it gets into the theory of relativity when we're talking about the speed of light. Now, just for those, so you can get an appreciation, okay, if you use miles instead of meters, because I know a lot of my audience is in the US here, this would be 186,000 miles, not per hour, but per second, right? So think about 186,000 miles, right? Usually if you travel from one end of the country to the other, you're maybe talking about several thousand miles. So think about 186,000 miles in 1 second. That's how fast light is going. That's incredibly fast, all right? So that's light. Now, what exactly is wavelength? Wavelength, think about a wave pattern that I have here, right? So if I take a look at this, wavelength is from the crest of one wave to the crest of another wave, just like this, right? So there's my wave, my light acting as a wave. This right here is considered the wavelength. This is denoted with lambda. And usually we measure wavelength in nanometers when we're talking about it. However, we will be converting back and forth to meters very often because the speed of light deals with meters per second, not nanometers per second. So you're going to have to pull out some of those old conversion factors, specifically nano, 10 to the 9th, right, when we're working with that, or 10 to the minus 9th if we're talking about meters. So then frequency is essentially how many times am I passing through a given point in time with that wave per second. So in other words, if I have a point right here and I have a wave that's passing through that point, right? So imagine this wave is continuing to oscillate through that point. The question is, how many times does the wave pass through that point in a given second? So per second, or sometimes you'll see that as second to the minus 1 when people write that. Okay, there's another unit for per second, which is also hertz. That's one that many people are familiar with. A lot of instrumentation that we use, we'll talk about hertz. When you get to organic chemistry, there's things like NMR, which is nuclear magnetic resonance, similar to an MRI in terms of the technology. And you use hertz when you're talking about the frequency of the radio waves that you're giving off there, and the magnetic fields. So hertz is a very common unit. It's per second. So think about this. We have nanometers, which could be converted to meters, and we have per second, which is hertz. So if I want to interrelate all of these, I can say that the speed of light is going to be equal to the frequency times the wavelength. So in other words, that's lambda times nu. So this is the first major equation that we are interested in working with here. Speed of light is equal to the wavelength times the frequency. And note that the units we're looking to use here is per second. So you again may see that as hertz. And the unit here is going to need to be meters. And that's because the speed of light is in meters per second, unless you find a different value for speed of light and change it into, nanometers per second or something like that. But by and large, most classes you're going to be in meters per second. That's how they're going to work with this. All right, so let's try to solve some problems with this as we relate it. And keep in mind, we'll talk about this at the end. We're going to talk about how energy relates to frequency, and that's going to start leading into the next lecture. All right, so let me look at my problem here. I've got two of them for us to work out. So I have that a green light, okay, is going to have a wavelength of, a green light has a wavelength of 522 nanometers. All right. So the question is, what is the frequency of this light? Now, I'm going to encourage you to work this out without watching the follow-through first, because that is how I always suggest you do it. You should try to practice without my help and then use my help as a guidepost in case you're lost here. This is just some simple algebra. There is a little bit of converting in it, so I'll let you know that. But let's see if you guys can do this. So I would suggest you pause the video, see if you can get through it, and then unpause it and come back. But I'm going to get working on the answer here, okay? So what you need to do, the first thing that you should be doing is taking your wavelength, which we know, and converting it into meters because it's in nanometers. We're going to need to use meters to get frequency. So 1 nanometer is equal, because I want nanometers to cancel, right, is equal to how many meters? That's the question. And 10 to the minus 9th meters is what that's equal to. You could also put that 1 meter is equal to 10 to the 9th nanometer. So you can put 10 to the 9th down here and 1 up here. That's how I usually teach students to work with it in the first place, so they don't get confused when to use negative exponents or not. All right, so you convert this and you end up with 5.22 times 10 to the negative 7th, okay, times 10 to the negative 7th meters. So this is the wavelength. This is lambda right here that we just solved for, right? Because that's what we had up here. We put it into meters. Now, why is it 10 to the 7th and not 10 to the 9th? Because 522 has a 10 to the 2nd built into it, right? 522, if I'm going to 5.22, that's got a 10 to the 2nd because that's in the hundredths unit. So when I'm looking at this, I now have my meters for my lambda, so I can use my equation, speed of light equals, and then I say lambda times nu, and nu is what we're looking for because we want the frequency here. So I'll algebraically rearrange this to give the speed of light over lambda is equal to nu, the frequency. So now I'm in business because I have all the units that I need properly set up. So I can say that 3.00 times 10 to the 8th meters per second over, and then I'm going to use the lambda, which is 5.22 times 10 to the minus 7th meters. Meters are going to cancel out with meters, and look at that. We get inverse seconds, which is exactly what we would expect for frequency. So continuing with this, go ahead and find out what this equals. And you should have come up with, let's see, 5.75 times 10 to the 14th. 5.7, sure we clearly show that point there. 75 times 10 to the 14th, and that is second inverse, or you could also say that that was hertz. Okay, so again, get used to using those as an interchangeable set of units. All right, so that's one problem. Let's give another one. Let's try to solve this time for the wavelength and see if we can do that. All right, so in this case, we're going to say, what is the wavelength of a wave that has a frequency, so of a wave with a frequency that is equal to, and what do I have here, 3.64 times 10 to the 7th hertz. Okay? So find what the wavelength is. Again, I suggest that you attempt this first without my help and then go through the walkthrough that we have here. So I'm going to go ahead and get started on the answer. The speed of light is equal to lambda times frequency. In this case, we have frequency, so let's rearrange this so that the speed of light over our frequency is equal to the wavelength. This is going to be in meters. All right. So you can solve for it in meters. I didn't specifically tell you what I wanted the unit in. Let's do meters, and we can also look at nanometers. Okay. So we know that C is equal to 3.00 times 10 to the 8th meters per second. And down here I have 3.64 times 10 to the 7th per second, right? So the per seconds cancel to just give me meters, and if I solve for that, I'm going to end up finding 8.24 meters. That should be the answer you found. Okay? So that's pretty large in comparison to the example that we were just doing, right? So the meters in the previous example was on a 10 to the minus 7th scale. That's very tiny compared to just the regular ones unit scale. So if I wanted this in nanometers, remember that meter is a larger unit, so I would need a lot more nanometers to make up a meter. So if I was interested in this in nanometers, I would say I need to take this times 10 to the 9th, so it becomes 8.24 times 10 to the 9th nanometers, which is a very large value. So there you go. All right. Now I did mention there's one other thing I wanted to talk about here, and what that is the relationship of energy to frequency and wavelength. So first of all, what you want to realize is that if I take wavelength times frequency, and here's the speed of light, okay, the relationship that these have to one another is that they are inversely proportional. Right? This is an inverse relationship, meaning as one of these goes up, the other one has to go down in order to maintain, because the speed of light is constant. Remember that. So what do we talk about in relation to energy here? Well, the easiest way to think about it is frequency. So think about waves. If the waves are long and slow like this, this would have a low frequency and a high lambda. Okay? Now, if I have another example, let's say I have one like this, right? So more rapid, in this case the frequency is higher because I'm passing through a point more times, right? Think about a slow one. I'm going very slow through a point over seconds. And then in a high frequency, I'm going through that point rapidly over some given amount of seconds. And so in this case, the wavelength would be lower with that inverse relationship. Well, that makes sense. Look at this. There's a nice big wavelength. Here's a tiny wavelength. If this is my point, I don't pass as many wave cycles through it in a second as if this was my point, where I have lots of these little wave cycles. And a lot of students confuse this relationship in terms of energy, but the number of times a wave can hit a given point, as that increases, the energy will also increase. So this example right here is high energy, and this example would be low energy. And students get confused because they see the giant wavelengths. They think, oh, the size of the waves are larger, therefore they must be stronger or higher in energy. That's not the case, because the strength of in terms of energy, the strength of the energy for a wave comes from how rapidly it can pass through a given point in a specific cycle, in a hertz, right? So right here, I can pass through a given point over a second more times than I can in the upper example, and therefore when we're talking about the energy associated with that, high frequency is going to have high energy, and low frequency is going to have low energy. Okay, so hopefully that makes sense to everybody. We will look at calculating energy in the next round, but that about wraps it up. I want to stop this video here because we're at about 20 minutes. So hopefully this has helped to explain the relationship between speed of light, frequency of a wave, and the wavelength of a wave, along with what quanta is and the idea of specific energy units. So that wraps it up. Thank you guys very much. Please remember to like, comment, and subscribe if you found any of this helpful. And I will see you guys for the next lesson. Take care.